In this video, we consider the one-loop renormalization of a scalar theory. In particular, we are going to consider the following action that we have already considered in some previous lectures. In particular, we have S, the action, sub lambda 0, where lambda 0 is the scale of our theory. This action depends on the field phi. Let me zoom out a little bit. And we can write this action in the following form: integral, and then we have 1/2 d phi squared, where as usual this is d mu phi, so this is just an abbreviation and shorthand for the tensor notation that you usually see. But anyway, d phi squared plus 1/2 m squared phi squared plus lambda over 4 factorial phi to the fourth d for x. This is the action that we consider. In particular, we are considering Euclidean geometry. So this derivative here is basically d1 phi squared plus d2 phi squared plus d3 phi squared plus d4 phi squared, and you can generalize this by means of a weak rotation also to the Minkowski metric if you want. But we will consider an Euclidean signature. The quadratic terms in phi, so the kinetic term is quadratic in phi, so here we have a derivative, but it is also quadratic in phi, and then we also have this other mass term. It contains this mass squared, and here we have phi squared. These quadratic terms receive quantum corrections from graphs with two external lines, and these corrections are computed by means of the exact propagator. Let's denote the propagator with this delta, capital delta of k squared. So this is the propagator in the frequency domain, and this is simply the Fourier transform d for x e to the I k dot x, and then here we have an average phi of x, phi of 0, like this. Some other times you might see instead of 0 here you might have y, and here instead of x you would have x minus y. But the result is independent of y. Now, classically, the function, let me denote it by f of x defined as phi of x, phi of 0 average, so in particular it's this quantity here, so it is the inverse Fourier transform of the propagator. So basically it is the propagator in the space domain. Now, this function f of x solves the equation minus del squared plus m squared f of x equal to delta of x. This is a four-dimensional Dirac delta, and basically this comes from the classical equations of motion. So you start from the equation of motion written in terms of the Lagrangian. So we have the derivative of the Lagrangian density if you want, but I will call it Lagrangian with respect to the field phi minus d mu dl d mu phi, like this. This is equal to 0 if, of course, x is not 0, because if x is equal to 0, you can see that the equation of motion here is equal to this Dirac delta, so it will give us an infinity when x goes to 0. In particular, you have to think that this is equal to delta of x1, delta of x2, delta of x3, delta of x4. So what do we mean by x equal to 0? We mean that x1, x2, x3, and x4 should all be equal to 0. Anyway, now in the Fourier domain, if we rewrite this left-hand side, We can also write integral d for k over 2 pi to the fourth minus the derivative operator becomes minus ik squared plus m squared f hat of k, which is the Fourier transform of f of x. But what is this? This is just delta, let's call it delta 0 of k squared. With this 0 here, this superscript means that we are considering only the classical contribution to the propagator. So remember that this equation here holds only classically. So we don't consider any quantum correction because this is the classical equation of motion if you think about it. But with the path integral, we don't have just one trajectory. We have multiple trajectories, and then we have to be careful because this equation is not in general satisfied. We cannot say that it is satisfied. Then here we have e to the minus ik dot x, and this is equal to delta of x. In order for this result to be equal to delta of x, we must make sure that this is equal to 1. And therefore, delta 0 of k squared, which is equal to half hat of k, should be equal to 1 over k squared plus m squared. And this is not surprising because it is a result that we also derived more rigorously in the previous lectures. In this case, we derived it by knowing that the classical equation of motion is given by something of this kind. If we seek to consider quantum corrections as well, now let's consider the following function that I will explain little by little, capital Pi of k squared. This function denotes the sum of all one particle irreducible graphs, 1pi, one particle irreducible graphs. These graphs consist of graphs that cannot be split in two by removing a single line. Now I will tell you more about this, and we will see it more clearly. In particular, delta of k squared will be given by a sum of different contributions. In particular, I'm going to denote them like this. First, we have this contribution, which is the classical contribution. It is just a line here, so this is the classical propagator. To this line here, we attribute the classical propagator, which is 1 over k squared plus m squared. And here I have phi at the end of this portion of the line, and here we also have phi at the end of this other portion of the line. Then we have higher order contribution, so here we have phi. Then here we have 1 pi phi, so this stands for one particle irreducible, and we attribute the function capital Pi of k squared to this block. And I will tell you more about it. But just wait a moment before the explanation. And then the other higher order terms are phi, 1 pi, 1 pi, phi, and you get the idea, right? So all the other contributions are given by more and more one particle irreducible graphs. Now, this will give us, if we write down the expressions, this first contribution will give us 1 over k squared plus m squared. This second graph will give us 1 over k squared plus m squared from this part of the graph, so this edge if you want, and also another contribution of this kind from this part of the graph, so we get this quantity squared. And then we also get the function of the one particle irreducible graph, which is just pi of k squared. Then if you want to write the contribution of this graph, this will be 1 over k squared plus m squared to the third power, and then we have pi of k squared squared, because we have two one-particle irreducible graphs, and then you have higher order contributions. Now you can rewrite this in the following manner. You can factor out 1 over k squared plus m squared, and then you have 1 plus, you have basically you can write a series of terms, sum over n from 0 to infinity, capital pi of k squared divided by k squared plus m squared, and this is raised to the power n, right? It's exactly coincident with that series of terms. And this is easy to calculate if we assume that pi of k squared is smaller than k squared plus m squared, right? So we can say that this summation will converge, and in particular it will converge to the following value. Here we still have this factor 1 over k squared plus m squared, and then we have 1 divided by 1 minus this term of the series, pi of k squared divided by k squared plus m squared. But this can be written in the following way. It is just 1 divided by k squared plus m squared minus capital pi of k squared. So you see that the corrections to the propagator are going to change this denominator here with this minus pi of k squared, where we wrote pi of k squared as a one particle irreducible graphs. So pi of k squared is related to one particle irreducible graphs. Now let's dig deeper into the significance of pi of k squared. Pi of k squared is known as the self-energy of the field. In perturbation theory, pi of k squared is given by, let me draw it like this. We have phi, then here we have 1 pi, one particle irreducible, and then we have phi. So in computing the one particle irreducible graphs, the two powers of phi are treated as an external source. And basically what we are going to get from this is the following. We get phi here, then we have a vertex, and here we have a loop. Inside the loop here you have to think that we have the field phi. Here we have phi, and then we have contributions of this kind for two vertices, one vertex here, one vertex here, and here we have two loops. So you can see that we are increasing the number of loops. So these are higher order contributions, but we can also have the following graph, phi, then we have an edge here, and then we have one loop like this, and inside the loop we have another edge, and here we have a vertex, and then here we have phi plus dot dot dot. To one loop accuracy, we only have this graph. And in particular, if we consider the loop, since phi here and phi here are just an external source, we have to consider the integral related to this loop. So we have one vertex, and to the vertex we associate the factor minus lambda. Then to the loop, we associate the integral d for p over 2 pi to the fourth, and then we have 1 over p squared plus m squared. So we have to integrate this propagator because the variable p is not defined inside the loop. So we have to integrate over all the possible values. And remember that we also have to divide by the symmetry factor of the graph, which is 2. So basically what we get, the contribution that we get is the following: minus lambda divided by 2 integral d4p over 2 pi to the fourth 1 over p squared plus m squared. And this is a contribution that we calculated in some previous lectures. So we calculated it from the path integral. And from the lectures, you can see that the derivation of this contribution is not so simple, not so straightforward. It is quite complicated, convoluted, because you have to perform several integrals and do some series expansions, and then you truncate the series to first order in lambda. And this minus lambda comes from expanding the action, in particular e to the minus the action s. So e to the minus s, you expand it in first order in lambda, and what you get is minus lambda times some integrals. So this minus lambda actually comes from expanding e to the minus s. Now, the integral is performed, so we will think that the integral is performed over those values of the magnitude of momentum p, or the energy. If we are working with units such that the speed of light is equal to 1, then momentum and energy have the same units. And we are calculating this integral for those values of the mode of p such that the mode of p is smaller than or equal to lambda 0, which is the scale of our theory. Now, if we go to spherical coordinates, we have minus lambda over 2, and then we get a factor integral over d omega. D omega is the solid angle in 4 dimensions. In 4 dimensions, we can call this integral d omega just omega 4. I will say more about this. Then we divide by 2 times 2 pi to the 4th, and then we have an integral of the following kind, p cubed dp, and then we divide by p squared plus m squared, and we integrate from 0 to lambda 0. So this p here is actually the mode of p, so the one that I have denoted like this here, whereas this d4p denotes dp1, dp2, dp3, and dp4. So p1, p2, p3, p4 are just the components of momentum, whereas here with p I mean the mode of momentum. Now this omega 4 in 4 dimensions can be obtained with some mathematical tricks, and you can find more on the appendix. But let me tell you that omega 4 can be calculated, and one can find that this is equal to 2 pi squared. And you can obtain this from the generic formula in n dimensions. So omega n can be found to be equal to 2 pi to the power n over 2 divided by the gamma function evaluated at n over 2. And let me tell you that you can find a simple derivation of this formula in the appendix, but I will not get into the details in this video here. Now, at this point, we can rewrite this integral by making a substitution. In particular, the substitution that we want to make is p squared equal to m squared u, and you can recast the integral in a different form, and you can integrate over the new variable u. The integral that you will find is a simple one, and what you are going to get is the following expression. So I will not do all the steps. What you are going to get is the following: minus lambda m squared divided by 32 pi squared, lambda 0 squared over m squared minus natural log of 1 plus lambda 0 squared over m squared, like this. Now you can see that we have a problem. We have a problem because as soon as we let lambda 0 go to infinity, you can see that this term diverges because the logarithm will grow to infinity, but it will grow much more slowly than lambda 0 squared here. So this term will go to infinity. And if we want to obtain finite results, then we must modify the original action to include counter terms. So in particular, remember that we started from the action s sum lambda 0 of phi, and this will have to become something like this: s sum lambda 0 of phi plus a counter term of the following kind: s ct phi lambda 0. So ct stands for counter term, and this action will depend on the field phi and also on the energy scale lambda 0. And we are going to define it in the following fashion. So s Ct phi lambda 0 is defined to be integral 1/2 delta z d phi squared plus 1/2 delta m squared phi squared plus 1 over 4 factorial delta lambda phi to the fourth d for x. Now we can think that these corrections that I labeled delta z, delta m squared, and delta lambda arise because we have integrated out high energy modes. So after the integration, the couplings in our theory are 1 plus delta z from here, and this one, remember, comes from the original kinetic term that we had in the action that we started with. So I'm really talking about this term here. So you can see that it is multiplied by 1 here, 1/2 times 1 times delta phi squared. So what we get in here is 1 plus this delta z, and then we have another contribution of the kind m squared plus delta m squared from this one. Then we have this delta lambda, so we have lambda plus delta lambda, right? Now the first order contributions to the propagator will come only from delta z and delta m squared, not from delta lambda. Why is that? Well, because if we expand the action e to the minus s, in particular, we expand it, because, I mean, delta z and delta m squared should be considered as small terms, right? Then we expand it in lambda, as you remember, and you can see that these quadratic terms will affect the propagator, whereas this quartic term will be a small correction to lambda. Anyway, the question remains, how do we choose the value for delta z, delta m squared, and delta lambda? Well, delta lambda will be something else that we will do at a later stage, because it will be a higher order correction. But about delta z and delta m squared, we can say something more, and this has to do with renormalization. We will find a way to choose their value by means of a so-called renormalization scheme, but we will do it next time.